So, guys, today what we're going to do is talk about radioactivity and nuclear. And the first image to show you is just the quintessential mushroom cloud from a nuclear device being detonated. This first slide here we'll actually go through in class together at some point. So, let me go and talk about radon. So, radon is actually fairly common in the Midwest. And what happens is it's a naturally releasing gas that certain houses can trap, and you need what's called a radon mitigation system. So Nebraska actually has relatively high levels of radon. And my guess is some of you that live in homes older than roughly 1980 have a radon mitigation system. Essentially, since the mid-'80s, homes are actually built to naturally mitigate radon. And so if you're ever at your house or if you ever go by a house and you see something that looks like this is basically like a radon mitigation system. And essentially how it works is there's a fan. And what happens with this fan is it essentially gets all the gases and stuff that would sometimes get trapped in the basement, and it just pushes that outside. So I actually have a radon mitigation system in my home. My home was built in 1962. And essentially what happens is that we tested the basement before we moved into the house, and it had high levels of radon. And so the seller of the house had to put in our mitigation system for that to happen. So first to talk about nuclear is just electricity generation. Obviously, the United States being a large country with a large economy and 350 million people, there's a lot of energy sources to use. I know this slide's slightly outdated, but the numbers are roughly about right. Most of our energy comes from natural gas and coal. So, for instance, MUD, which brings water and gas to our homes to like heat our furnaces, water heaters, and things like that, is natural gas. And then most of the electricity that we get in Omaha comes from coal burning power facilities. Next on the list will be nuclear, and then all the other items here. Again, wind and solar have definitely increased a little bit in the last 4 or 5 years, but it's still fairly minor compared to the overall pie that you would get. This just shows nuclear production by region and by area, so you can kind of see how that looks. And then also the generating capacity of nuclear power in major countries. The United States actually has the most nuclear generation compared to other countries out there. But when you actually compare it by percent of nuclear, France is number one. And what's very unique about France is that in the 60s, 70s, and 80s, all the major political parties coalesced around that they wanted France to be a leader in nuclear energy. So it didn't matter which party was actually in charge. They all kind of strive to make that happen. And you can see when you do by percent, the United States falls down. Again, there's a lot of factors for that. We have a lot of coal. We have a lot of natural gas. Some of the nuclear disasters have definitely pushed people away from wanting nuclear in the States. And so that's why we've kind of lagged behind, some of the other countries, mostly in Europe, for that. Now, a big question comes up: why are things radioactive, and what does that mean? So, what happens is all elements can fall in what's called the band of stability. And what happens with that band is that if an element's within it, it's going to be a stable atom. So it will not undergo radioactive decay. It'll just hang out, things like that. The issue you run into is if it's above the stable band, it's naturally radioactive, and it's going to undergo radioactive decay to become more stable over time. So this here shows the band and then the type of decay that you would actually get from that. And we'll spend time on all these four parts. And so what I mean about the band and being nuclear stable and how that's set up. So we've talked about before how the nucleus has protons and neutrons. And there's this force called the strong nuclear force that keeps the nucleus together. If the ratio of protons to neutrons is 1 to 1 or 1.5 to 1, you'll have a stable nucleus. If it's below or above this ratio, it's going to be unstable and then more than likely undergo radioactive decay to become more stable. So you can see here, helium has a ratio of 1:1. And I talked about higher or lower. Bismuth is the last stable element. Bismuth, that has 200. Bismuth basically has 200 and so we have an element of bismuth and it has 206. What's going to happen is 206 minus 83 is 126. 126 divided by 83 gives us about 1.52 to 1, which is going to be stable. What happens is that the atoms that are unstable will undergo set nuclear processes to get the nucleus more stable. So if the element is above the band, so the ratio is higher than 1.5 to 1, it's going to undergo alpha or beta decay. If the element's below the band, it's going to undergo positron emission or electron capture. This here just shows alpha, beta, and gamma. Alpha is the weakest, beta is slightly stronger, and then gamma is the strongest. I have this chart here just comparing the three. So alpha particles always have a charge of a +2. The description is they're usually kind of like a helium nuclei, where we have 4/2 for helium. The penetrating power is roughly paper. Beta is going to be stronger. It can roughly go through metal foil, and it basically is a negatively charged electron. Where gamma is super high, and that's the one we usually worry about because gamma radiation can cause cancer. You can see it can go through concrete, and it's small enough and powerful enough that it can disrupt DNA and create problems. So the first one I want to talk about is alpha. So we can see alpha, and it produces a helium. So what's going to happen if you're doing a nuclear equation and you have an alpha decay? You're going to take 4 away from the mass and 2 away from the number. And so you'll have 2 protons and 2 neutrons happening from that. So this is a nuclear equation. We're just showing the nuclear equation for decay of radium-226 to radon-222. And very similar to a chemical equation, everything has to balance in a nuclear equation. So the atomic mass on top has to balance on the left and on the right. And then the atomic number on bottom also has to balance on the left and on the right. So on the top here, we have 226. So you have 222 and 4. That'll get us 226. You have 88. We have to have 88 on the right. So 86 and 2 gives us 88. So that way it balances left and right. So you can see this. What I would like you guys to do is go and perform alpha decay on PO 208. So go and pause the video, do that, and then I'll have it on the next slide. Okay, so as I indicated, we're doing alpha decay on 208, PO 208. So 208 is the mass, atomic mass. 84 is the atomic number. I always like to put the alpha symbol or the helium atom first so I know what I'm changing. Then what's going to happen is 208 minus 4 gives me 204. 84 minus 2 gives me 82. And when I look at the periodic table, the element with the atomic number of 82 is lead, or Pb. So therefore, you'll have 208 over 84 PO goes to 4/2 helium plus 204 82 Pb. Very similar as a chemical equation, if you have these two flipped, so if you have the lead first and the helium second, that will also be okay. You just need both items located on the correct side of the equation, and again, everything needs to balance. Beta radiation or beta decay is the next one. And so what occurs is you have a beta particle. With a beta particle, it's not going to change the atomic mass, but it will change the atomic number by a -1. So the atomic mass is going to stay the same, but the atomic number is actually going to go up by 1. And so what happens in beta decay, which is real interesting, is a neutron actually turns into a proton, and then it ejects a beta decay. So this diagram here just shows this nucleus and this ejection of that beta decay. And when we look down at the neutron, we're going to get this neutron is going to turn into a proton. We're going to get some beta, and we're going to get some gamma radiation that's going to come off of that. So that's how iodine is going to undergo beta decay. We're going to have, and it's 131 iodine. You'll have 131, and then the atomic number for iodine is 53. And then you're going to undergo beta decay, and you'll have 131 over 54 equals Xe. And then again, what's going to happen is since one electron is going to come off, these have to balance. So you're going to have 54 plus a negative 1 gives us 53. So that's balanced. And then we have 131 plus 0 equals 131. So that's balanced there. This is what this would look like. Again, if you wanted the beta item first, that's fine. It would be always 0, negative 1. It'll be an E, or it'll have the beta symbol for it to make that work. What I'd like you to do now is go ahead and pause the video and go ahead and do beta decay for carbon 14 or C14 in your notes, and then I'll have the answer on the next slide. All right, so for 14, 6 over carbon, what's going to happen is we're going to have beta decay, so I'll have a negative 1 over here. If I have 6 here, I need to have 7, because 7 plus negative 1 gives me 6. And 14 and 0 gives me 14. So when I look at the periodic table, the item with atomic number of 7 is nitrogen for that. So that shows beta decay. And again, as you can see, you're bringing that ratio down by changing the number of protons, either changing the number of neutrons or the number of protons, so that way the ratio gets closer to 1.5 to 1. So gamma radiation is very penetrating, very high energy. It is produced with either alpha or beta, and it's highly dangerous. There's no change to the atomic mass or the atomic number, and normally we don't show gamma radiation when it comes to these decays. So the deal is, and it's real crucial to understand this, the atom undergoes these radioactive decays to become more stable. And then unfortunately, gamma radiation is just a byproduct of that, and humans are susceptible to gamma radiation that can cause cancer, and that's why we're worried about radioactive decay, because some radioactive decay will cause issues or problems. Okay, so just to recap the first part. Stability determines decay. If it's stable, it will not decay. If it's unstable, it will. We talked about alpha and beta, which are the ones above 1.5. Now we're going to talk about positron and electron capture, which are the ones that are below 1. So with positron emission, it's the same mass as electron, but with a positive charge. So basically, you'll have a proton that then is going to turn into a neutron and give off a positron with that. So the atomic mass is going to be the same. The atomic number is going to go down by 1, and then you're going to have a positron that's going to be emitted. So what's going to happen is carbon, which has 6 as its atomic number, it undergoes positron emission. One of those protons is going to move to a neutron, and then so 6 minus 1 gives us 5, which then makes it boron. And so that's what's going to happen there. Again, as I said, same mass, atomic number goes down by 1, and the positron's emitted. You can write this up as a chemical equation. So if you have a positron emission for potassium 37, you'll have 37 over 19, because 19 is the atomic number for potassium. If you're going to do a positron emission, it's going to be 0, then you're going to have a plus over here, plus 1 for an E. And then what's going to happen is 19, so 19 plus 1 gives, 18 plus 1 gives us 19. 37 plus 0 gives us 37, and we're balanced. And then because you're going to 18, that's going to be argon over there. Electron capture is essentially an electron gets brought into the nucleus, and it combines with a proton to form a neutron. So the atomic mass is going to be the same, but the atomic number is going to go down by 1. So what's going to happen here, if we have beryllium-7 and we're going to do electron capture, beryllium is going to go from having an atomic number of 4 to an atomic number of 3, and then we'll end up with lithium-7 at the end. Showing this diagram here for electron capture for argon, if I have argon-38, and it's undergoing electron capture. Again, this is the only one where the electron is going to go on the left side of the equation. All the others, alpha, beta, and positron, go on the right side of the equation. We'll have 38 and 0 gives us 38. 18 minus 1 gives us 17 for Cl. Again, I copied this from a book, so it shows gamma radiation for this one. You do not need to show this. If you just have 38 over 18 Ar plus 0, negative 1E goes to 38, 17 Cl, you're good. This diagram here just shows the type of decay, just kind of like wrapping that up. The particle, whether it's emitted or absorbed, you can see 3 of them are emitted, 1's absorbed. The mass change, and then the atomic number change for that to happen. You guys will want to be familiar with these 4 atomic types. I will quiz you on these and test you on these, so you'll have to be very well versed when it comes to this. But these items, we'll work on this, and it should be good to go. And this will line up with the nuclear worksheet that'll be done later on for the course. Again, to talk about radioactivity, you got to talk about decay rates. And so half-life is just a term to mean the time required for the substance to decay in half. So strontium-90 has a half-life of 29 years. So we start with 10 grams of strontium. How long will it take to only have 1.25 grams remaining? Well, to break this problem down, if the half-life is 29 years, and we have 10 grams going to 1.5, we need to half the amount of strontium until we get to 1.5. Then that will determine how many half-lives we've gone through, and then we can determine how old the specimen is. So if you look at this first one here, I go from 10 to 5, so that's half. For this one here, I go from 5 to 2.5, also half, and then half of 2.5 is 1.5. So when I add the number of half-lives, 10 to 5 is 1, 5 to 2.5 is another 1 for a total of 2, and 2.5 to 1.5 is another 1 for a total of 3. So because we have 3 half-lives, and each half-life is 29 years for this particular element, that means that the fossil is 87 years old. So radiometric dating is how we actually date fossils. And so why we're very confident in the fossil record for our planet is due that every fossil has different elements that are radioactive that are undergoing decay. And by analyzing those elements, because they're resistant from temperature or pressure or time change, it's a very consistent process. We can utilize this. So carbon dating used to be the first one when we would look at organic substance. Organic just means life. So you're made of organic material, plants, your dog, your cat. We're all carbon-based. And so if you were to happen to become a fossil, one, that would stink, but if you were to become a fossil, the amount of carbon-14 in your body would slowly break down, and then we could determine when roughly you passed away if you were dug up thousands of years later. So carbon-14 has a half-life of 5,730 years. We usually use it to date items for about 24,000 years, up to 24,000 years. What we found out is all items have uranium-238, and they undergo decay to go down to lead-206. And because uranium-238 has a half-life of 4.5 times 10 to the 9 years, you can date any fossil out there and get a very accurate measurement on how old that fossil is. This diagram here just shows radioactive dating. You have this living thing, it dies, small piece of it becomes that, it goes stable to unstable, and then from that we can determine. Moving into nuclear. So there's different reactions that can occur when it comes to nuclear reaction. So nuclear reaction is you have atomic nuclei and it's changed into others. Transmutation means changing of one element to another. All nuclear reactions are a transmutation. And then induced transmutation is artificially created. I think induced transmutations are pretty cool. So basically what happens is that you take a stable element and you basically fire items at it to try to make it unstable. So in this one here, we have bombardment of nitrogen 14. And literally, you're just shooting alpha particles at this thing to try to slam into it and make a new element and make it unstable. And so from this bombardment here, you can make fluorine 18 that then will decay down to get us oxygen 17. Again, if you look at the periodic table, the radioactive elements are higher than 93. So if you notice on the periodic table, as we go down to 92, I'm sorry, all the radioactive elements that are higher than 93 are created by induced transmutation. That's what I was trying to articulate. So the periodic table in my classroom, and I'll point this out, all the natural elements are basically colored black. They're naturally occurring in solids at our conditions. They're blue at their naturally occurring elements and liquid in our conditions, which are only bromine and mercury. And then the ones that are red, like hydrogen, oxygen, and argon, are going to be gases under our conditions. Those are red. If you notice from 93 on, the ones on the periodic table in my class are outlined. And the reason why they're outlined is because we have created these elements. They're artificially created by slamming nuclei into it and creating new things. The periodic table I have is actually slightly outdated. We actually have filled in everything to 118. So like the one I have goes to 112, and there's a space, and then 114, and then a space. So that periodic table I got about 13 years ago, and since then we've filled in all of basically period number 7 for that. So let me show you transmutation here. Here's this massive transmutation thing. Again, I will never have you guys do this on a quiz or test, but this just shows the different spaces for this. So again, for radiometric dating, you can see this is uranium-238. It's going to undergo all these different decays. And then at the end of this, we're going to have a stable lead atom that's going to come out of this. It's always good to talk about nuclear fission versus fusion. So fission is when we break down nuclei. And so all nuclear power plants or nuclear weapons are based upon that. You break down nuclei to get this chain reaction. Fusion is nuclei forming together, which is what the sun does. So our sun, our star, and our solar system is a controlled nuclear reaction. It's taking hydrogen, fusing it together, and giving us helium. And then the byproducts of that are light and heat, which we value here on Earth to keep all living organisms going. So this just shows the reaction in the sun, what occurs when that happens. So this is an overview of radioactivity. We'll cover more of these items, the nuclear reactions, the concepts and things for that. But this is kind of the meat and potatoes when it comes to the notes. And we'll move on from there. All right. Good job, guys.